can get something useful out of my talk today. So today I'm going to talk about using machine learning to explore the chemical space. And to set the stage from a little bit of pragmatic point of view, the ultimate goal of chemical science or material science is really to discover novel molecules and materials with the desired properties. And here, the materials could be molecules, as you can see here, for example, antibiotic molecule that has been approved and actually developed by LG company in Korea. Or it also could be crystal structure, shown here, one of the lithium battery materials. And in achieving this goal of discovering new materials with the target properties, the use of data is often referred to as chemical informatics or materials informatics. So the goal of materials informatics is really to understand the structure property relationships of the materials using data. And so therefore, basically, you have a mapping between the structure and property. And when you go from structure to property is something like going from cause and effect. Here, the structure would be the cause and the property would be the effect. Or you could start with defining the property that you want to achieve first, and then design a structure that would have such a property, and that can be an inverse design problem. And so overall, the idea is to use this informatics to dramatically reduce time and cost for novel discovery of molecules and materials. In this data-driven materials design, there are several ingredients. Actually, there are three that are most important. One is data, because data is all that you learn from. And the second, you need to have a way of representing the data. And if you have data and a good way of representation, then you can perform simple regression or sometimes complicated regression for property prediction. And once you have a way of predicting the properties, the next step is to explore the chemical space to find the target material with the target property. And this second step would be arguably much more difficult because when you talk about chemical space, it's really a space of atoms and molecules connected to bonds with bonds. So it's really an infinite space. And exploring such a vast space for finding a target material, it could be quite difficult. So today I'm going to talk about a couple of aspects that we recently addressed to sort of enhance the accuracy of property prediction and also a way of exploring the chemical space more efficiently. Like I said, once you have the data, so in my talk, I'll assume that you are given data. And once you have data, the next step is to represent the molecules and materials. And depending on how you represent the molecules and materials, the prediction accuracy could dramatically change. The reason is because, for example, if you use some kind of feature engineering, then you basically use simple attributes of the molecules, such as electron negativities, electron affinities, and so on. And those features should change once you want to predict a different property. So that's why the representation is important. And for example, on the right-hand side, I'm showing you a couple of examples of feature engineering in catalysis applications in which absorption energy prediction is the most widely used target task. And you can see that CO or other binding energies can be predicted reasonably well with electron negativities, d-band width, and so on. However, like I said, this feature-based engineering is useful and they could offer insights, but they should change if you want to want to predict the properties, different properties, because they should be represented with different physics. And so a more general way of representing the molecule would be graph-based representation. It's similar to the use of Hamiltonian that we use in electronic structure calculations. So in those calculations, no matter what property you want to calculate, you start with the geometry of the molecules. So this kind of structural encoding or graph neural network is the one that I'm going to talk about briefly today. And in graph neural network, you basically represent the atoms and as nodes and chemical bonds as edges. And neighboring atoms information actually is transferred to the central atom via a mathematical operation called convolution. And if you apply these convolutional operations many times, then you basically encode the entire structure of the molecule. And as you can see at the bottom of this slide, this graph-based neural network has quite promising accuracy, HOMO-LUMO, enthalpy, formation energy, bulk modulus across molecules and crystals. So, and this is sometimes called the message passing neural network because the information of the neighboring atoms is transferred to different neighboring atoms. So this is good. However, there are several major challenges of this graph-based neural network for various property prediction. First of all, most of these properties are predicted on the optimized geometries. In other words, you need to perform the geometry optimizations using DFT first. So that's one bottleneck. And in other words, there are no graph-based neural network that can actually allow the force calculations at the moment in the current implementations. And another aspect is that all of these methods are deterministic. In other words, if you put in one geometry, then the model spits out one number. But of course, we know that the model usually has uncertainty, and it'd be good to have uncertainty quantification. So this is our recent work in which we try to predict the absorption energies without geometry optimizations. The idea is that we take the bulk structure and then cut the surface along a particular facet. And then in usual situations, you would put an adsorbate on top of that and perform the geometry optimizations. But we bypass that and we label the binding atom as a pseudo atom and then encode that using graph convolutions and try to predict the binding energies using the model. And the performance is described at the bottom of this slide, and the existing model by Udelsi and Grossman both require surface structures and adsorbate relaxed structures. But our model does not require neither of those information, but the mean absolute error is comparable or sometimes better than the existing models. And this has been trained and tested based on about 20,000 absorption energies. And so we think that this could be one practical way of using machine learning for catalyst applications. And in fact, this label side representation work was motivated by this experimental work by Duan Group UCLA and Bill Goddard at Caltech. And this is the figure I shown on the top is the Jagged platinum nanowire. It's a platinum nanowire with very rough surfaces. And this Jagged platinum nanowire has been shown to demonstrate, enhance the hydrogen evolution kinetics. But the mechanism was still unclear. But to understand the mechanism, one needs to evaluate the activity of every single site of this Jagged nanowire, which has about 4,000 platinum atoms and 20,000 active sites. And so we needed a simple model that can estimate binding energies, and that was the motivation of the of this previous work. Anyway, so we used that model to study that, and we calculated the current density as a function of potential, and the resulting curve from simulation agrees reasonably well with experiments. And from that, we could understand to some extent what the mechanistic origin of the catalytic enhancement was. And then the second aspect of graph convolution, like I said, was the uncertainty quantification. On the left-hand side, like I said, conventional neural network is deterministic, but once you have several models, then you can sort of measure the uncertainty using the variance of different models, and that's what we did. And if you allow this uncertainty to be quantified, then you can increase the discoverability of the new materials by more than a factor of 2. Okay, so far I've talked about property prediction aspects of machine learning using data and representation. But like I said, once you have this property prediction model, the next step is to explore the chemical space to identify which molecule or material would have the desired property. Roughly speaking, in this slide, we have categorized 3 different strategies, the inverse design strategy into 3 different strategies. The first one is most intuitive and easy to understand, namely high throughput virtual screening. So here, basically, you take the existing database, say that includes 20,000 molecules, for example, and evaluate the functionality of each molecule one by one, and to see if there is any candidate that meets your need. So it is essentially an exhaustive search, but within the database that you have chosen. It is exhaustive, but the bottleneck, the downside is that you cannot go beyond the database. So once the target material is not in the database, then there is no chance that you can find the material that you want. The second strategy is global optimization. And there are many algorithms out there to perform global optimization. And one perhaps most widely used one is evolutionary algorithms. And what's different in the global optimization from the previous high-throughput virtual screening is the fact that global optimization actually utilizes the prior visits. So they learn from prior explorations. And so you can think of global optimization, it could be to be slightly more efficient than the high-throughput virtual screening. And the third strategy is the generative model. And this generative model is different than the first two in the sense that in generative model, you basically take the database and learn the distribution of the entire database. And once you have the distribution, then you can sample from the distribution to find the new material. And therefore, in generative models, you can sort of explore the space between the 2 existing molecules and materials. You can sort of explore the hidden portion of the space because you can sample from the distribution. And therefore, also in generative models, you can go beyond the existing database. All you do is learn the distribution and the sample. So today I'm going to focus on the third strategy, generative model. Like I said, in generative model, all you do is take the database and learn its distribution. And once you learn the distribution, the next step is just to sample, and that's a new material. Of course, along the way, you need to sort of link the structure with the function in a separate network. There are several generative models out there, but here I am showing you one example. It's called Variational Autoencoder. the architecture of the variational autoencoder is shown on the left. So you first encode your molecule in some kind of representation. In this case, SMILES strings representation. So benzene is C1, CCCC, C1. And your representation molecule is encoded into usually a smaller dimensional space into Z. So Z is your latent space, so-called. And that vector is then decoded back to the original molecule back. So you basically encode your molecule into a smaller dimensional space and then restore the information back to the original molecule. So by itself, you have not done anything because you start with the benzene molecule and end up with the benzene molecule back. But what you're left with is the latent space, which we denote as Z here. And Z is a continuous space. So I'm sorry, I don't have the pointer, but on the right hand side, you see two-dimensional sort of a projection of the latent space, and each dot is a data point. Each dot is a molecule, for example. And because this is a completely continuous space, you can perform some kind of steepest descent gradient method optimization. And so on the right bottom panel, you see that although you start with a molecule with 18.06% of drug likeness, whatever the measure is, but then you can do perform the optimization, then you end up with a molecule with 98th percentile category. So that shows that once you have this continuous latent space, you can sort of optimize the molecule because it's continuous. So that was the work by Asperger back in 2018, and we want to have a solid state version of that, but solid state material is different than molecules because it's periodic. So anyway, so we had to represent the molecule, the solid state material that is fully invertible, meaning that once you encode the molecule material, then that material should also be converted back to the representation back and forth. So on the middle of the slide, I'm showing you the latent space of solid state vanadium oxide compounds. Each dot is a material, and so this is latent space. And so to demonstrate that our model can generate the sensible materials, what we have done was that we excluded the actually experimentally synthesized materials and then train the model without them, and then see if our model can rediscover those materials. That's what we did as a validation. And we find that out of 31 that has been excluded from training, we were able to rediscover 25 of them using this generative model. And so because you have this latent space, we can then sample latent space and decode it back to the material, then that's a new material that hasn't been discovered. So that's what we did, and the results are here. And on the left bottom corner, I'm showing you the phase diagram. I'm sure most of you are not familiar with this kind of phase diagram, which I was not either previously. So on as x-axis is the vanadium atomic fraction, and y-axis the formation energy. And I'm showing you the blue solid line at the bottom as convex hull. You can think of it as a stable phase line. Anything that are on that line are stable phases. Anything that are beyond that straight lines are metastable. And you can see that the blue dots are the existing materials, and the orange dots are the newly discovered materials in our work. And you can see that these four compositions are completely new compositions that hasn't been discovered previously, and many of them are very close to the convex minimum phases, meaning that they are quite metastable, and they might be synthesizable. And right bottom are the actual crystal structures that we've discovered, and they are perfectly normal looking, as you can see, with sometimes space group as well. And so I'm now going to describe another generative model, which is called GAN, and that is based upon the game theory. But bottom line is that the GAN is another flavor of a generative model, and here we are applying that GAN model to manganese magnesium oxide chemical composition space. So on the left-hand side, I'm showing you the phase diagram of MgMNO using the materials that you can find from the materials project database. So these red dots and white dots are all from the existing database. And on the right-hand side, I'm showing you the same phase diagram. They are filled with the structures that were generated using our model. You can see that our model can fill the gaps between the two existing materials. And so that's why I mentioned at the very beginning of this talk that these generative models allows us to explore the hidden portion of the chemical space. And using these newly discovered materials, then you can see if any of them could be potentially useful for some energy applications. So I'll skip that because that might be too specific. And so these generative models really allow us to explore the hidden portion of the chemical space and allow us to generate new structures. However, we all know that most of those structures will not end up with synthesis. Most of them will be discarded. And so our next question then was, can we have a model that can predict the synthesizability of those materials? And this synthesizability prediction is a practically important task, but technically challenging because unlike all other learning tasks that I have talked about so far, in which you have the true answer and you teach the machine to learn the true answer and the wrong answer. And but for the synthesizability, for those materials that have been synthesized, you know that they will be synthesized. But those that have not been synthesized, you cannot say that they will not be synthesizable, because it could simply mean that you haven't been able to synthesize, but somebody else might. So this is not a conventional supervised learning. So this is only partially supervised because you only have partial answers for the partial selection of the materials. So I'm not going to talk to you about the details of the algorithm, but through the iterative processes, you can learn the synthesizability using only the partial true answers. So here you have, from the materials project database, you have 50,000 positive data, meaning that 50,000 already synthesized materials. And then you have 80,000 unlabeled data, meaning that 80,000 materials that have been obtained using substitution of the existing synthesized materials, but you don't know whether they might be synthesized or not. So basically you have 50,000 positive data and 80,000 hypothetical data. And so the performance is on the left top corner. You see that the model predicts about 87% of the time the synthesizable materials is synthesizable. So the accuracy is about 87%. And another validation, so as a validation, what we did was that we trained the model using the synthesized materials up to the year 2015, and to see if the model can predict the materials that have been synthesized between 2015 and 2020 as synthesizable. And we see that, again, about 86% accuracy. One thing that we found quite interesting was the plot on the bottom left. You see that, so CL score, that's the score that we defined, namely crystal likeness score. So any material with crystal likeness score beyond 0.5 is synthesizable in our model. Anyways, so if you look at bottom left corner, then synthesizability score and thermodynamic stability has almost no correlation. In other words, very stable materials are not synthesizable, and sometimes very metastable materials are highly synthesizable. So thermodynamics is not always equal to synthesizability. And then as a further validation, then we, out of 80,000 unlabeled hypothetical materials, we took the top 100 scoring materials and see if any of them has been reported to be synthesized, although they have not been deposited in the database yet. And we find that actually 71 out of 100 the top scoring materials have indeed been synthesized and reported in literature, though not deposited in the database. So this is a good validation of our model. And you can see that our structure and literature structure are almost one-to-one mapped identical. Okay, so that's the end of my talk. So to summarize, because it's data that the model learns from, data is most important. And I talked about a couple of aspects, property prediction and generative models for invoice design. But for the bubble, so we have not demonstrated yet any of these generative models actually ended up with actual synthesis of those materials with the target property. So this experimental demonstration is very important, I think. So Juhan, Kunho, Jidon, and Sungwon are the very bright students who did all the work, and Alan, Zach, Bill, and Tao are my collaborators for the subject that I talked about today. Thank you very much for your kind attention.
Thank you, Professor Jung. So it's time to take some questions. Any questions? I don't see any in the chat window. Let me ask, who's that? Oh, there's a waving here, okay. Okay, Pablo Joao. Can you invite him over?
Hello, can you hear me?
Great, yes, we can. Please go.
So thank you very much for the great talk. I have a question about variational autoencoder. So when you have this latent space, it's continuous. So I assume that two very close points on this latent space correspond to the same structure, right? So you could split this space into areas corresponding to each structure. But then the question is what happens on the border of these areas?
That's a great question. So what you're basically referring to is this ideal situation that we are hoping for. So ideally, we would like the latent space to be structured so that one regional space has a similar structural sort of motif, for example, and another region, with another structural motif. However, that's not always the case because it's a really high dimensional space. And so not even talking about this boundary of the two regions, but the two structures sometimes can be nicely interpolated with structural sort of a nice transition, but also depending on how you interpolate between the two structures in this high dimensional space, you might see some sudden jump in the structures. But when we do this spherical interpolation, we see a smooth transition, but we never really talk about the boundary because it's